In the last class we ended when we were looking at G by RT, and we were looking at getting the other 4 functions. Remember, there were 5 other thermodynamic functions which are not so easy to measure. We are trying to express that in terms of P, V and T. They are U, S, H, A and G, and we started looking at G by RT. The reason for that will become apparent in a little while later, either in this class itself or the next class. We started considering G by RT, and then from G by RT we got the other 4 U, S, H and A. Let us go through it once again for completeness. We saw that by considering G by RT as a function of pressure and temperature alone, we could get this V by RT as dou of G by RT by dou P at constant T, which is what is here, and H by RT as this is minus H by RT squared, and therefore if you are going to replace this with the partial differential, it would be dou G by RT by dou T at constant P, and that would be minus H by RT squared, and therefore H by RT is minus of T of the partial differential. And so we are done with V. H, V is an additional thing here, and we also found that from the original definitions we could write U in terms of H and PV, which in turn were written in terms of G by RT earlier, and S by R could be written in terms of H by RT and G by RT. If you look at it, we have V by RT here, H by RT here, and U by RT as well as S by R. Therefore, we have a complete set of thermodynamic variables if we know G by RT, and for that reason this G is known as the generating function. The Gibbs free energy is known as a generating function. We use it in the form of G by RT here. Let us continue and get back to write proper residual properties now. Let us consider equation 327. I am going to present it here again, we do not have to go back now. D of G by RT equals V by RT dP minus H by RT squared dt. This was equation 327. If we write this for an ideal gas, then this becomes D of G ideal gas by RT equals V ideal gas by RT dP minus H of ideal gas by RT squared dt. Let us call this equation 332 to be in line. 327 came a little earlier, equation 332 is the next number in sequence. Now, if we subtract 332 from 327, note this is the actual value, this is the ideal value, and therefore actual value minus the ideal value must give us the residual value. Therefore, D of GR, the residual by RT equals V residual by RT dP minus of H residual by RT squared dt. Let us call this equation 333. Earlier we considered GR, rather G by RT as a function of P and T and derived the other thermodynamic functions. Now, let us consider GR by RT as a function of P and T and let us write the corresponding terms. Okay. What I would like you to do is take maybe about 5 minutes and do this exercise. Consider GR by RT as a function of P and T, consider the total derivative in terms of the partial derivatives, and therefore write the functionalities of the partial derivatives in terms of the thermodynamic variables that we need. and thus establish that you could use GR by RT to generate the other thermodynamic functions. Go ahead, maybe you want to take about 10 minutes since you are looking at this for the first time, take about 10 minutes and do it. Go ahead please. Let us continue. This was in the same vein as earlier for G by RT. Instead of just the actual values, we have the residual values here. Therefore, the same argument holds. See whether you got this. If you did not get this, go back again and look at how we obtained the relationships for the actual values. Vr by RT equals dou Gr by RT dou P at constant T. Let us call this equation 334, and HR by RT equals minus T dou Gr by RT dou T at constant P. Essentially this comes from just expressing the total derivative in terms of the partial derivatives for an exact differential and writing the partial derivatives as equivalent to the thermodynamic functions. The last equation, let us call that as equation 335. Now, when an experiment or a process takes the system, let us say from state 1 to state 2, and let us say that this is performed under constant temperature. Okay, we are imposing the condition of constant temperature for this process. In such a case, we can use the equation 334, which is essentially an equation where the partial derivative is taken and the temperature is held constant. Let us take a look at that. 334 here, Vr by RT equals dou P of Gr by RT at constant temperature. Therefore, if we perform an experiment under constant temperature conditions, you can use this equation directly to get this from this. And we can use that to calculate the residual Gibbs free energy from the PVT data. Let us take a look at that right now. dGr by RT equals Vr by RT dP at constant temperature. The other derivative at constant temperature goes away because that goes to 0, rather the dt term goes to 0, and therefore the other term drops out. Under these conditions, integration of this equation, integral of dGr by RT is nothing but Gr by RT, and if we integrate this side, let us say from P reference to a certain pressure P2, Vr by RT dP. From an earlier equation 324, we know that Vr, it is essentially the residual property of V, the molar volume, the actual volume minus the ideal gas volume, which we said was equal to V minus RT by P, because ideal gas molar volume is RT by P, and which when expressed in terms of the compressibility factor becomes RT by P Z minus 1. This we saw in equation 324 itself. If we substitute this in the previous equation for Vr, we get Gr by RT equals integral from P reference to P2 Z minus 1 dP by P. We will call that 336 equation, and the value of P reference is usually taken to be 0, which is fine, and if that is the case, then you can design suitable experiments to obtain the terms on the right hand side of this equation 336, which can in turn be used to calculate Gr by RT, the residual Gibbs free energy. And from the earlier equations, we could relate the Gibbs free energy, the generating function, to get the other thermodynamic variables U r, S r, H r, and A r, and from the residuals you can get the actual quantities. Some other residual properties can be obtained as follows. Just I am going to explain whatever I said in brief earlier. Equation 335 directly gives an expression for HR, the residual enthalpy. HR by RT equals minus T dou dou T of GR by RT times P. Therefore, once we know GR by RT, we can get HR by RT from this expression. Let us call that equation, rather we had already called it 335. GR by RT we have already seen as P reference to P2 integrated of Z minus 1 by P dP, and if we substitute equation 336 for GR by RT into equation 335 to get HR by RT, we get into this situation. Dou GR by RT dou T at constant P equals dou T of P reference to P2 Z minus 1 dP, Z minus 1 by P dP. I would like you to ponder over the right hand side of this. Have you seen such expressions earlier? What is so special about that? Okay, take a couple of minutes to ponder about this, and then I will come back and tell you how to handle this. Okay, hopefully you would have seen that it is a derivative, a partial derivative of an integral here that we have here. How do you do that? There is something called a Leibniz rule, which you would have encountered in your first or second course in mathematics in your first year, which allows us to differentiate an integral. Nevertheless, that Leibniz rule would have been written for a total derivative, and what we have here is a partial derivative. If it had been the total derivative, whatever you had learnt from the first year course would have sufficed to do this. You might have forgotten it, you might want to go back and verify how to do a differentiation of an integral, but that does not matter. Here you have a partial derivative, and therefore you need to consider it further, and there is something called a generalized Leibniz rule, and what it says is that you can look through this in probably some specialized books in mathematics. What it says is that the partial derivative can be handled in a similar fashion to the total derivative according to the generalized Leibniz rule. Therefore, whatever you did for the total derivative of an integral can be done for the partial derivative of the integral too, is what this says. And therefore, dou T of integral P reference to P2 Z minus 1 by P dP at constant pressure can be written as, recall the Leibniz rule, this was integral between the same two limits. You take the derivative inside the integral dou T of Z minus 1 by P at constant P dP, this is the first term, plus the function evaluated at the upper limit times the derivative of the upper limit with respect to dt, which is the function here with which it is differentiated, therefore dt of P2 minus the value of the function evaluated at the lower limit times the derivative with respect to t with respect to this variable of the lower limit, which is P reference. Okay, so this is exactly the same form that you would have learnt in your earlier mathematics class. Now take a look at this. This is fine, we will come back to this a little later. This is d dt of P2. P2 is a particular pressure value. Similarly, P reference is a particular pressure value, in this case it happens to be 0. Therefore, we are actually doing the differentiation of a constant, therefore, these two terms go to 0, and therefore, these two, the second and third terms on the right hand side are actually 0. Therefore, dou dou t of P reference to P2 z minus 1 by P dP at constant pressure reduces to integral of P reference to P2 1 by P dou z dou t at constant P, which is what this one reduces to. You have if you take the derivative here at constant P, that reduces to this. Please verify this. I am not going to give you extra time here, but we can go back after the class and verify this. P integral of P reference to P2 1 by P dou z dou t at constant P dP. Therefore, HR by RT, which is what we started looking at, and we went into all this Leibniz rule business because we wanted to differentiate an integral to get HR by RT from GR by RT, and this is, as we know from the expression earlier, minus T dou dou T of GR by RT at constant P, and if we substitute this, we would get minus T from here times P reference to P2 1 by P dou z dou T at constant P times dP. Therefore, HR by RT can be evaluated from minus T integral of P reference to P2 dou z dou T at constant P into 1 by P dP. So, we have gotten HR by T or HR in terms of easily measurable properties. Let us call this equation 337. Now, the term inside the integral here dou z dou T is actually evaluated at constant pressure, but we began by considering experiments at constant temperature. Remember, the second term went off when we considered the process at constant temperature, therefore, dt went to 0 and so on. So, we began by considering experiments at constant temperature, but this is still valid by using one of our usual arguments. The state, although the state variables will not change along the will not change with the path chosen, the experiments need to be performed along a path. Experiments are based in reality and therefore, are path dependent, and therefore, to ensure the validity of the equation, the data needs to be obtained from a different experiment or from an appropriate mathematical expression. Okay. So, the dou z dou T at constant P data needs to be obtained from a different set of experiment, not the same constant temperature experiment. That will not be valid here. I think I should mention this again. This is a slightly different way of presenting the same basic argument. Here we are in the realm of experiments which are grounded in reality. We are looking at ways to get dou z dou T at constant P, whereas we started the derivation by looking at constant temperature process. And since the experiments are path dependent, we need to obtain dou z dou T at constant P from a different set of experiments where the P is held constant. Now, using equation 331 for residual properties, we can get the other variables. SR by R equals HR by R minus HR by RT minus GR by RT. This we have already seen earlier, and we have an expression for HR by RT which we just derived by going through the differentiation of an integral and so on. and we also have an expression for gr by RT in terms of the measurable properties. Therefore, if we substitute both of them here, we have SR by R equals HR by R is minus T integral of P reference to P2 dou Z dou T at constant P into 1 by P dP minus GR by RT that we already seen earlier, P reference to integral from P reference to P2 Z minus 1 by P dP. Therefore, we have SR in terms of T, P, Z and so on. We will call this equation 339. Now, we have residual properties starting with gr by RT, and hopefully we would have generated the other residual properties, and we know that the actual property minus the ideal property or ideal gas property is the residual property, and therefore, if we have expressions for the ideal gas values, then we can get the actual values from the residual values. Therefore, let us see the obvious thing. The actual property is nothing but the residual property plus the ideal gas property. For a process between states 1 and 2, delta M or M2 minus M1 is nothing but delta Mr plus delta M of an ideal gas, and note that the thermodynamic properties are state functions. This is repeating the earlier argument, but in the context of this process. Thus, the experimental conditions employed, say constant temperature, are irrelevant to the actual process, actual values. The values depend only on the state and not the path followed, for example, the experimental conditions employed between the states. But also note that the values are with respect to a particular reference state, which must be explicitly defined. That we know right from the beginning, but it is good to remind ourselves from time to time, so that we do not forget it when we actually need to use it. So, let us look at the second part now. We had the residual properties evaluation in terms of P, V, T, Z and so on. Now, let us look at how to get the ideal gas values in terms of the easily measurable quantities. The ideal gas values can be evaluated as follows. Equation 248 gave us dH equals Cp dt plus V minus T dou V dou T at constant pressure, the whole dP. This we have already seen. Now, since we are looking at ideal gas, we can use the relationship P V equals R T. Therefore, dou V dou T at constant P, right from here becomes R by P. You can see how to go about doing it. At constant pressure, you can take pressure out constant, and dou V dou T at constant pressure would turn out to be R by P directly from this equation. Let us call that equation 340. Now, the second term on the right hand side of 248 will go to 0 for an ideal gas, and therefore, dH ideal gas is Cp ideal gas dt alone. You do not have this for an ideal gas. Why? Because you have this V minus T, and you substitute R by P here, you get Tr by P, and Tr by P is nothing but V, V minus V goes to 0. Therefore, you end up with dH ideal gas is Cp ideal gas dt, equation 341. And equation 250 from the earlier module, it gives us ds equals Cp dt by T minus dou V dou T at constant pressure dP. You can go back and check if you want. This is essentially what 250 gave us, and substituting equation 340 in 250 in terms of dou V dou T at constant P and so on, we get ds equals Cp ideal gas dt by T minus, we have already shown that dou V dou T at constant P was R by P. So, we substitute that here R by P dP, we will call that equation 342, and therefore, we have ds for an ideal gas in terms of easily measurable quantities. Now, let us look at some process values between point 1 to point 2 that the system takes during a process. H2 minus H2 equals H2 ideal gas plus H2R, that is from the definition, and H2 ideal gas we have seen is nothing but integral of T reference to T2 Cp ideal gas dt. This directly comes from the definition of Cp plus H2R. We will call that equation 343, and H1 similarly can be written as T reference to T1 Cp ideal gas dt plus H1R. You know where we are going, we are going to take the difference now, 343, 344, and delta H, which is H2 minus H1, can be written as Cp ideal gas dt integrated between T1 and T2. Note, one was from T reference to T2, the other one was from T reference to T1. You subtract the two, effectively you are subtracting the areas, therefore, the limits change to T1 to T2, plus of course H2R minus H1R. Let us call that equation 345. Similarly, using 342 that we have shown earlier, ds equals Cp ideal gas dt by T minus R by P dP by P, and therefore, for a process delta S is integral of T1 to T2 Cp ideal gas dt by T minus R, this is remember R P by 1 by P dP, the integral of that is going to be ln of P between the limits, and therefore, you get minus R into ln of P2 minus ln of P1, which can be written as ln of P2 by P1, plus of course S2R minus S1R. This is essentially the ideal gas property, and we are trying to find out the delta S or S2 minus S1. Therefore, you have these two terms here, and let us call this equation 346. The above equations for the thermodynamic properties U, S, H, A, G or V can be written in terms of reduced properties also, and therefore, the number of measurements or the number of data points that you need from existing values becomes much less, becomes much easier to evaluate. And as mentioned earlier, when generalized properties are used, the equations become generalized, in other words applicable to all gases, and one therefore does not need the PVT data for specific pure substances to estimate the thermodynamic properties. So, essentially what we have done so far is to look at generating the not so easy to measure thermodynamic variables U, S, H, A and G from measurable, easily measurable quantities, but we focused on G to begin with. We got G in terms of the value, in terms of the easily measurable properties, then we got everything else. To do that, we had used the residual properties formulation, and then we said that we are going to look at things in terms of reduced properties, and in such a case you do not need specific PVT data, the correlations that are given would be applicable to almost all gases in general with a few exceptions. And so, let us look at those generalized correlations to the extent possible today. From the definition of the reduced properties, we can of course write our PR, if you recall, is nothing but the ratio of P to PC, and therefore, P is nothing but PC into PR, and therefore, dP is PC is a constant. So, PC times dPr. Similarly, T is nothing but Tc Tr, because T by Tc is the definition of Tr. Therefore, dt is nothing but Tc times dTr. Now, if we substitute the above in the following equations, these were the equations that we obtained earlier for Gr by Rt equals integral of P reference to P2 z minus 1 by P dP. This was equation 336 earlier. H by Rt was equal to minus T into integral of P reference to P2 dou z dou T at constant P dP. This was equation 337, and Sr by R equals minus T integral of P reference to P2 dou z dou T at constant P dP by P minus integral P reference to P2 z minus 1 by P dP, equation 339. Why do not you go ahead and substitute in the remaining time? We have about 6 minutes left. In the remaining time, why do not you substitute PCPR wherever P occurs, TCTR wherever T occurs, and see what expressions you get in terms of the reduced quantities. Go ahead please, we will take it off from here, continue from here when we meet next. See you in the next class.